Now we're going to do an example using that head loss equation that we just derived in the prior lecture. So this is taken from Professor White's fluid mechanics book. Give him credit for this example. So we're going to have gasoline. It's at 20 degrees Celsius. It's flowing through a pipe. It's a smooth pipe with a 12 centimeter diameter that is 10 kilometers long. And the gasoline is flowing at a rate of 75 meters cubed per hour. The inlet pressure at the pipe is 24 atmospheres, and the outlet pressure is 1 atmosphere, and there's an elevation change. The pipe goes up so that the outlet is 150 meters higher than the inlet elevation. So we're being asked to estimate the friction head losses. So that was that term H friction in that prior equation. Those are the friction head losses. And we are told that the density of gasoline, obviously we could look this up, is 680 kilograms per meter cubed. So we're going to go ahead and do this using that head loss equation. So I'll write that down here. Now you guys could stop the video and try this yourself if you want. So I'll pause here for a second so you can turn it off. Okay, you're back. Maybe you didn't go away. But if you did go away, let's see how you did. So we're going to go ahead and write the head loss equation. So I'm going to go ahead and write P over rho G plus V squared over 2G plus Z in is equal to P over rho G plus V squared over 2G plus Z out. And then I have my 3 head loss terms, H friction, which is the one I'm actually trying to find, H pump, and H turbine. All right, well, there is no pump in this problem, so that's gone, and there's no turbine in this pipe either. So the pipe has no turbine and no pump, so those 2 terms are going to go away. So I'm just going to be left with the other terms. So now I'm going to rewrite all this, and I'm going to try to solve it for H friction, whereas I've been asked to find the friction head losses. So rewriting that equation, for H friction, I get H friction is equal to, I gotta make sure my signs are right, so I still have left side P over rho G plus V squared over 2G plus Z at inlet, and then I'm going to be subtracting out, because it's come over from the same side, the outlet P over rho G plus V squared over 2G plus Z all at the outlet. Okay, so that's my formula, and I can solve that. I'm going to rearrange this a little bit so it's a little easier to see what's doing what. So I'm going to have H of the friction is equal to 1 over rho G times P in minus P out, and then 1 over 2G V squared in minus V squared out, and then I just have Z, Z in minus Z out. So that's my formula to calculate this. And you can think about this for a second. This term's 0. Like, I could find the velocity if I wanted to, but the velocity in and the velocity out are going to be the same. Why is that? Well, it's a conservation of mass. The conservation of mass says that, m dot equals rho AV. Well, rho isn't changing for the gasoline. I'm treating it as an incompressible liquid. A isn't changing because the pipe diameter doesn't change from the inlet to the outlet. The inlet and the outlet both have the same pipe diameter. So there's no change in that. Therefore, there can't be any change in V. So rho AV is going to be rho AV, and V is going to be V, and they're going to be 0. So their subtraction is going to be 0. So I just have the pressure change and the height change to worry about. And I know all those numbers. So it's H friction is equal to, I'm putting my 1 over rho G. 1 over rho is 680 kilograms per meter cubed. Of course, G is 9.81 meters per second squared. That's that. Now my pressures, I have 24 atmospheres, so that's 24, sure I get my decimal right, 000 newtons per meter squared minus 1 atmosphere, 101,000 newtons per meter squared. That's my pressure change. And then I have my Z change, which is 150 meters. So that's what I was told. It's elevated to 150 meters. So easy there. And Z out, but Z out is greater than Z in. So this is going to be a negative 150 meters because Z out is bigger than Z in. Okay, so I turn the crank as it were, and I have that H friction is equal to 348 meters minus that 150 meters, which is 198 meters. So that's the answer. The head losses from friction are 198 meters. So that is why some engineers like this type of notation where you count these losses as basically an equivalent of loss of height. The amount of energy we lost through friction was the amount of energy it would have taken to raise that gasoline another 200 meters in elevation. This is an approximation, as we said. We're still doing control volume analysis. So that means we don't know any details about the flow. But the only place we really used that approximation was in velocity, because the velocity is not really uniform at the inlet and the outlet. But we don't really use that because the velocities actually cancel, and there's no real reason to think the velocity at the inlet and outlet would be any different from each other. So this is probably pretty darn accurate if you wanted to just calculate the friction losses for this particular type of flow in a long pipe.